Hello and welcome to Unit 6, Part C. This is going to be about error and about confidence intervals for a difference of proportions. So let's begin. All right. We're going to test random samples. 90% are produced. The null hypothesis is that they're equal to 90. And the other would be that greater than 90. That's what we get from this problem. And we're looking for which of the following describes a type 1 error. So type 1 error means that the null is true, but the test came back evidence to reject it. All right, now this happens a certain percentage of the time, whatever your significance level is. Significance level is 5%, which typically is if we drop below 5% of a sample occurring, then we say this is evidence that something's going on, and we reject. However, that happens purely by chance 5% of the time, whatever your significance level is. So a type 1 error is when the test came back and dropped below 5%. However, that was just a chance happening. So that can happen. So a type 1 error is that the null is actually true, but there was evidence for the alternative. And that would correspond with C. The test provides convincing evidence that it is greater than 90%, but the actual is equal to 90%. So that can happen. Type 1 error, the probability of a type 1 error is whatever your significance level is alpha. Probability of type 1 error is alpha, as we've said it. Number 2. Okay, we're setting up. The null is the percent of defective parts is at least 2%. So usually we do equal, but they did at least 2. I guess they can do that if they want. In FRQs, it'll always be equal. The percent of defective parts is less than 2%, which the following describes a type 2 error. So now type 2 is the opposite. Type 1 was the null was true, but there was evidence for the alternative. So the evidence for the null, but the alternative is actually true. So in this scenario for type 2, the evidence for the null, so our test is going to come back and the sample is not going to be significant. However, the sample is just strange, and it should have, if we took another sample, it probably would have came back as the alternative being true. So which of the following describes type 2 error? There's evidence for the null, but in reality, we should have found evidence for that's type 2, which corresponds with C. There's not evidence to reject. The test does not provide convincing evidence that it's less than 2%. But in reality, but the actual percent is 1%. But in reality, it is less than 1% or less than 2%. So C is the corresponding value for that. C, which of the following is defined as the significance level of a hypothesis test? It's our alpha. And alpha is also the probability of a type 1 error. Alpha, significance level, probability of type 1 error. Beta is the probability of a type 2 error, which we haven't yet really. There's something called power of a test, and we're going to get into that after Christmas break. So we're actually going to skip question 4, 5, and 6 because those are talking about beta and power. So we're actually going to pick up on question 7 here. All right, the null hypothesis. The more consequential error would be that the drug is effective. Okay, so they set up the null is that it's not effective. The alternative is that it is effective. The more consequential error would be for the drug to be effective, but the test does not detect effective. So that means there's evidence for effective when in reality, it's true that it's not effective, because then you're giving people this drug that everyone thinks that it's not effective, I guess, when in reality it is effective. All right. So they found the cure to the disease, but the test came back as it didn't cure the disease, I guess. So that's where we're at. So which of the following to avoid a more consequential error? They want to accept H naught when H naught is. So there's evidence for the null when in reality the null is false. That's a type 2 error. So they want to decrease a type 2 error, which means they want to increase a type 1 error. Okay, decreasing type 2 means you increase type 1. So that's new, and that's something, again, we'll talk about a little bit. So I'm overstepping my bounds here just a little bit. But if you want to decrease type 2, you increase type 1, which means we need to increase our significance level. Increase the significance level to increase the probability of type 1 error. All right, number 8. They gave us the null is not effective. The alternative is effective. The more consequential error would be that the diagnostic tool is not effective, but the significance test indicated that it was. Okay, so the bad error here would be there's evidence for the alternative, but in reality, the null is true. So that would be the type 1, and that is a type 1 error. So in this case, the type 1 error is the bad error. It's more consequential than type 2. You decrease a type 1 error. So to decrease a type 1 error, you decrease your significance level, decrease alpha, which corresponds to D on this one, decrease significance level. On to difference of proportions, estimating the difference of proportions. All right, so a research facility designs rockets. From a random sample 40, we get 14, that's our first proportion. And then from a random sample 30, we get 9, that's our second proportion. So we have two samples going on here. So right off the bat, take away A and B, because we are using. The researchers want to estimate the difference in the proportion, in the true proportion of the engines. So we're estimating a population proportion. We're not estimating a sample proportion. So take D out. And want to estimate the difference in a proportion, a difference in a proportion. So not a population proportion, but a difference in a population proportion. So E is the one we're looking for this one. Number 10. And it all has to do with the sample. The intent is to estimate a difference in the population proportions, not the sample proportions. 1 and 2 were good. And these are all categorical so far. Anytime we're dealing with proportions, like the proportions of Democrats in Indiana, it's categorical. You're either Democrat or Republican. You can't find the average of a Democrat. So in the future, we will do numerical, and that's called T instead of Z. We're going to do what's called a T-test and a T-interval when we're dealing with numerical data. So for now, we're dealing with categorical. Which number 11, random sample of 100 people. Country S had 15 with blue eyes. So the sample of S, 1.5, the proportion. Or another way to think of that, for our first population, N1 at 100 and 15, X1 is 15, we're going to plug this in our calculator. The second sample from country B had 25 out of 100. 25 out of 100, this will make sense in a moment. This is our confidence interval for a difference in proportions. Confidence interval. You take your point estimate for the difference, which is a sample minus sample, plus or minus the critical value, which for us is 95, so 1.96 for that. And then it's your standard error right here. This is your standard error for the difference of these proportions. And you plug it in, you do all your work, you get this, so you get this value, which is D. The other option, so that you don't have to do work and save yourself some time, is that you get your calculator out and you do confidence intervals, 2 sample proportion Z interval. We'll get to T's in a moment, in a little bit, 2 sample T interval. We will do those. So X1 was 15. There's 15 successes out of 100. In the second sample, there was 25 successes out of 100. And we have everything we need. And it gives us our lower bound, negative 0.21, and our upper bound, 0.01, which is interesting. If we were to have this come back as a real sample here, anything in this interval is plausible at the 95% confidence level, which means it's plausible to say that P1, PS minus PV here is less than 0 because negatives are in that interval. So it's plausible to say that, which would imply that the probability in country S is less than the probability in country B. However, 0 is also in this interval. So it's also plausible to say they're equal, which would imply this. So it's plausible to say that there is no difference in proportions, to significant difference in proportions of country S from country B. This difference of 15 to 25 people just happened purely by chance, I guess. It's also plausible to say, because there's a positive number here, that this is true. And so really, you can't really tell much from this, but that is the confidence interval right there. If it all came back negative, then, or if it all came back positive, that tells us something for sure. Next, random sample. 240 adults over the age of 40 found that 140 use online dating service. So 140 out of 240 use online dating. And another sample showed 234, 131 out of 234 would use online dating. Okay, so we got 2 samples. There is a little bit of a difference in these samples. Is that difference, I don't know, is there something going on there? What is the so let's estimate the true difference based off of these samples. So you have a point estimate plus or minus value times our standard error. So you get your point estimate, which would be 0.6 minus 0.56 right there. Plus or minus the z-score for the 90% confidence interval. And then this is your standard error. It's 0.6 times 1 minus 0.6, and then you get 0.56 times 1 minus 0.56, which are these. Now this all corresponds to, this is the margin of error. That's what B is. B is the margin of error. They just want the what do they want? They just want the standard error, which is just this part, which corresponds with A as that. And then the rest are just 13. They're checking the large counts conditions for a difference in proportions is what they're doing here. Which of the following conditions for inference was the biologist checking? The large counts conditions, which corresponds with E. That is not about being random. It's not about the 10% thing. It's not about the population of deer. It's about the difference in the populations of the deer, the sampling distribution of the difference. That's what we're looking for. For number 14, same idea. Why is it not appropriate to use a 2 samples Z interval? It does say random there and there. I think we can go ahead and assume that 90 and 83 are less than 10%. So that's not the problem. D is not the problem. E doesn't matter. They don't need to be the same size. So really, we're looking at B and C as our answers for this. And what the problem is that in the first sample, n times the sample proportion is 5. And then the second sample, n times the sample proportion is 3, which are both less than 10, which means the samples aren't large enough. The samples are not large enough distributed. The normality of the sampling distribution in the sample proportions cannot be established. That's what we're looking for. And hey, that's it.